Hey guys, tonight we're embarking on a journey far beyond the cozy confines of Earth, venturing into the frigid, alien embrace of some of the most captivating celestial bodies in our very own solar system. Imagine for a moment, if you will, floating weightless through the inky blackness, the Earth a shrinking blue marble behind you as you hurtle towards distant worlds. Worlds that are not planets, but their silent, ever-present companions, moons. Can you truly picture that vast emptiness, the stars like scattered diamonds as you approach a new, uncharted frontier? We're talking about places so wildly different from anything you've ever known, so extreme in their environments that the very thought of life thriving there might seem like something ripped straight from a science fiction novel. And let me tell you, if you were actually there, exploring these places without the benefit of a heavily shielded spacecraft, you probably won't survive this. The vacuum, the radiation, the unimaginable cold, it's all part of the charm. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Now, dim the lights and let's ease into tonight's journey together. Our first stop on this grand tour is Europa, one of Jupiter's 4 largest moons, often referred to as the Galilean moons, named after Galileo Galilei, who first observed them in 1610. Now, Europa, from afar, looks like a perfectly smooth, slightly cracked billiard ball of ice. But don't let that serene exterior fool you. Beneath that frozen crust, scientists believe lies something truly extraordinary, a vast, salty ocean, perhaps twice the volume of all of Earth's oceans combined. Think about that for a second. More water than we have here, but hidden, trapped beneath miles of ice. It's like finding a secret swimming pool under your neighbor's perfectly manicured lawn, except this pool is planetary in scale and probably holds more mysteries than 1,000 ancient shipwrecks. This ocean isn't just a whimsical idea. There's compelling evidence. The surface of Europa is crisscrossed with reddish-brown lines, some winding for hundreds or even thousands of kilometers. These aren't just cosmetic blemishes. They're thought to be cracks and fissures in the ice shell, caused by the immense tidal forces exerted by Jupiter's colossal gravity. Imagine a constant cosmic tug-of-war, stretching and compressing Europa, generating enough heat to keep that deep-seated water liquid. It's similar to how kneading dough warms it up, but on an astronomical scale. You'd think all that stretching and squishing would make for some pretty wild ice quakes, and you'd be right. What kind of groans and cracks would you hear if you were standing on that shell? Now, why is a subsurface ocean so exciting? Well, on Earth, where there's liquid water, there's often life. And not just any life, but a diverse array of organisms, from microscopic bacteria to colossal whales. The theory goes that if Europa has liquid water, and if that water is in contact with a rocky core, which is also believed to be the case, then there's a potential for hydrothermal vents on the ocean floor. Here on Earth, these deep-sea vents, spewing superheated mineral-rich water, support entire ecosystems that thrive without sunlight, relying instead on chemical energy. It's a bit like a cosmic pressure cooker, creating the perfect conditions for chemistry to happen, and maybe, just maybe, for life to spark. Historians still argue whether the discovery of hydrothermal vents on Earth in the 1970s truly revolutionized our understanding of life's potential origins, but it certainly opened our eyes to possibilities beyond surface-level photosynthesis. It truly broadened our cosmic horizons. The idea of alien fish swimming in a Europan ocean might sound like pure fantasy, but the conditions are surprisingly favorable. We're talking about a world where the surface temperature hovers around minus 160 degrees Celsius, minus 260 Fahrenheit, which is cold enough to freeze your breath before it even leaves your lips. Yet, deep beneath that incredibly thick protective ice, there could be a warm, chemically active environment. It's a curious contrast, like finding a bustling, vibrant nightclub hidden beneath an abandoned snow-covered igloo. The sheer resilience of life, even here on Earth, in extreme environments, from boiling hot springs to the deepest ocean trenches, gives us a glimmer of hope for Europa. One quirky tidbit, some scientists even speculate that the plumes or jets of water vapor observed erupting from Europa's surface might offer a tantalizing opportunity to sample the ocean's chemistry without having to drill through miles of ice. It's like the moon is occasionally offering us a little sip of its secrets. Imagine that cosmic delivery service.
So, you've got this vast, potentially warm, and chemically rich ocean on Europa, tucked away under its icy shell. But what about the energy needed to kickstart and sustain life? That's where Jupiter's incredible radiation belt comes in. Now, you might think of radiation as a bad thing, and for us squishy humans, it absolutely is. But for the building blocks of life, it can be a powerful force. This radiation constantly bombards Europa's surface, breaking apart water molecules and creating oxidants like hydrogen peroxide and oxygen. These highly reactive chemicals can then be transported down into the ocean through cracks in the ice, providing a potential source of chemical energy for life, much like photosynthesis does on Earth. It's a bit like having a cosmic battery charger, constantly zapping the surface and preparing ingredients for whatever might be stirring below. Imagine that perpetual energy infusion, a constant cosmic spark for potential biology. Of course, the big question remains, has life actually started there? That's the million-dollar, or rather billion-dollar question that future missions aim to answer. NASA's Europa Clipper mission, for instance, is set to launch in 2024 and will conduct detailed reconnaissance of Europa, investigating whether it has the potential for life. It won't be drilling through the ice, but it will be making multiple close flybys, gathering data on the composition of the ice shell, the characteristics of the ocean, and even looking for those elusive plumes we just talked about. It's like sending a highly advanced detective to sniff out clues without ever needing to break into the safe. A mainstream historical fact here, the concept of panspermia, the idea that life might exist throughout the universe and is distributed by meteoroids, asteroids, and planetoids, even touches upon the idea of life potentially originating elsewhere and being carried to places like Europa. Though for Europa, the focus is more on in situ origins. It really makes you ponder the cosmic conveyor belt of life, doesn't it? Moving on from Europa, we shift our gaze to another tantalizing moon in the outer solar system, one that's also famous for its plumes, Enceladus, a small icy moon orbiting Saturn. If Europa is the mysterious, silent deep-sea explorer, Enceladus is the flashy show-off, constantly spewing jets of water vapor and ice particles into space from its south pole. Imagine a miniature extraterrestrial Old Faithful, but instead of hot water, it's spitting out what could be the ingredients for life directly into the vacuum of space. It's truly a sight to behold, even if you're just seeing the artistic renditions. These geysers, discovered by the Cassini spacecraft, originate from 4 prominent parallel fractures near the moon's south pole, affectionately nicknamed tiger stripes. And much like Europa, the presence of these plumes strongly suggests a subsurface ocean. But unlike Europa's global ocean, Enceladus's ocean might be more localized, concentrated beneath the South Polar region where the tiger stripes are. The plumes are not just water vapor. They also contain salts, silica nanoparticles, and organic molecules, including methane, carbon dioxide, and various hydrocarbons. This cocktail of ingredients is incredibly exciting because it points to active hydrothermal activity on Enceladus's seafloor, similar to what we discussed for Europa. It's almost as if Enceladus is waving a giant cosmic flag saying, "Hey, look at me! I've got all the right stuff for life." What an inviting cosmic billboard! The mechanism driving these plumes is also tied to tidal heating from Saturn. As Enceladus orbits Saturn, the gravitational pull varies, causing the moon to flex and stretch. This constant kneading generates heat within its core, melting some of the ice and creating pockets of liquid water. This water then seeps up through cracks to the surface where it erupts into space. It's a delicate dance of gravity and geology, perfectly orchestrated to create a habitable environment. One quirky tidbit about Enceladus is that the material ejected from its plumes actually helps feed Saturn's E-ring, making it visibly brighter. So Enceladus is not just a potential cradle of life, it's also a cosmic garden hose watering one of Saturn's glorious ring features. The presence of silica in the plumes is particularly significant. On Earth, silica nanoparticles are typically formed by hot water reacting with rock. Finding them in Enceladus's plumes suggests that its ocean water is indeed in contact with a rocky core, and that hydrothermal vents are likely active down there. It's almost as if Enceladus is waving a giant cosmic flag saying, "Hey, look at me! I've got all the right stuff for life." What an inviting cosmic billboard! The mechanism driving these plumes is also tied to tidal heating from Saturn. As Enceladus orbits Saturn, the gravitational pull varies, causing the moon to flex and stretch. This constant kneading generates heat within its core, melting some of the ice and creating pockets of liquid water. This water then seeps up through cracks to the surface where it erupts into space. It's a delicate dance of gravity and geology, perfectly orchestrated to create a habitable environment. One quirky tidbit about Enceladus is that the material ejected from its plumes actually helps feed Saturn's E-ring, making it visibly brighter. So Enceladus is not just a potential cradle of life, it's also a cosmic garden hose watering one of Saturn's glorious ring features. The presence of silica in the plumes is particularly significant. On Earth, silica nanoparticles are typically formed by hot water reacting with rock. Finding them in Enceladus's plumes suggests that its ocean water is indeed in contact with a rocky core, and that hydrothermal vents are likely active down there. It's almost as if Enceladus is waving a giant cosmic flag saying, "Hey, look at me! I've got all the right stuff for life." What an inviting cosmic billboard! The mechanism driving these plumes is also tied to tidal heating from Saturn. As Enceladus orbits Saturn, the gravitational pull varies, causing the moon to flex and stretch. This constant kneading generates heat within its core, melting some of the ice and creating pockets of liquid water. This water then seeps up through cracks to the surface where it erupts into space. It's a delicate dance of gravity and geology, perfectly orchestrated to create a habitable environment. One quirky tidbit about Enceladus is that the material ejected from its plumes actually helps feed Saturn's E-ring, making it visibly brighter. So Enceladus is not just a potential cradle of life, it's also a cosmic garden hose watering one of Saturn's glorious ring features.
So, Enceladus isn't just a pretty face with its tiger stripes and icy plumes. It's practically screaming about the potential for life. The presence of organic molecules, the evidence of hydrothermal activity, and the sustained liquid water ocean beneath its surface make it a prime candidate for astrobiological exploration. Future missions, perhaps even landers designed to taste those plumes, could directly sample the ocean's contents, giving us a clearer picture of its habitability. Imagine a tiny probe zipping through space, then delicately catching a few cosmic snowflakes from Enceladus's geysers. It's like having the moon deliver its secrets right to your scientific doorstep. What an incredible delivery service that would be! Now, let's journey further out, away from the immediate gravitational embrace of Saturn to its largest moon, Titan. If Europa and Enceladus are the watery enigmas, Titan is the oddball, the one that truly stands apart. It's the only moon in our solar system with a dense, substantial atmosphere, so thick in fact that it completely obscures the surface from our view in visible light, making it look like a hazy orange-brown marble. This atmosphere is primarily nitrogen, much like Earth, but with a significant amount of methane and other hydrocarbons. It's a bit like Earth, but if our atmosphere was a thick, smoggy soup of natural gas and the rain tasted like lighter fluid, you wouldn't want to breathe it, trust me. Could you even imagine stepping into that dense, cold mist? What really sets Titan apart, though, are its methane lakes and rivers. Yes, you heard that right. Lakes and rivers made of liquid methane, not water. At Titan's frigid surface temperatures, around -179 degrees Celsius, 290 Fahrenheit, water ice is as hard as rock, while methane exists as a liquid, forming entire hydrological cycles, complete with clouds, rain, and surface features that eerily resemble Earth's rivers, lakes, and even coastlines. Imagine standing on a shoreline, watching waves lap against a sandy beach, but instead of water, it's liquid natural gas, and the rocks around you are made of solid ice. It's a truly alien landscape, yet surprisingly familiar in its geological processes. A mainstream historical fact is that the Huygens probe, part of the Cassini-Huygens mission, successfully landed on Titan in 2005, providing us with the first direct images from its surface and confirming the presence of liquid on its surface. It was like finally drawing back the curtain on a stage that had been hidden for eons. The thick atmosphere and the complex chemistry happening within it make Titan a fascinating place for astrobiologists. While liquid water is considered essential for life as we know it, some scientists ponder the possibility of exotic life that could use liquid methane as a solvent instead of water. This is a truly wild concept, stretching our imaginations beyond Earth-centric definitions of life. Could there be organisms that breathe hydrogen, consume acetylene, and excrete methane? It's like asking if a fish could survive in a desert, utterly unthinkable under normal circumstances, but on Titan, perhaps not entirely. One quirky tidbit about Titan: its atmospheric pressure at the surface is actually slightly higher than Earth, meaning if you were there and wearing a very good spacesuit with a heating system, you wouldn't need a pressurized suit, just one to keep you warm and supply you with oxygen. You could theoretically just strap wings to your arms and fly, given the low gravity and dense atmosphere. Sounds like a blast, right? You could literally just jump and float for a while. The ongoing search for extraterrestrial life on Titan focuses not on this moment having life in its methane lakes, but on its potential as a laboratory for complex organic chemistry. The presence of abundant hydrocarbons, the interactions between the atmosphere and the surface, and the active meteorological cycle all contribute to a dynamic environment where complex organic molecules can form. These molecules are the building blocks of life, and Titan is essentially a planet-sized organic chemistry experiment happening in real time. Historians still argue whether the discovery of complex organic molecules in Titan's atmosphere was more significant than the confirmation of its active methane cycle for understanding prebiotic chemistry. The thinking is that if life could form somewhere without liquid water, Titan would be the place to look for the precursors. It's like finding all the ingredients for a magnificent cake, meticulously laid out, even if the oven isn't quite hot yet.
The potential is palpable. What secrets do you think those orange clouds are hiding?
While Titan's potential for exotic life in its methane seas is a truly mind-bending concept, the more immediate focus for astrobiologists is on the potential for a subsurface liquid water ocean beneath its thick ice shell. Yes, even Titan, the king of methane, might be hiding a more Earth-like secret. The idea is that deep beneath its icy crust, internal heating from the decay of radioactive elements and tidal forces from Saturn could keep a layer of water liquid. If this is true, then Titan offers a dual possibility for habitability, one for life as we know it in a deep water ocean, and another for truly alien life in its surface methane environments. It's like finding a secret warm swimming pool underneath a frozen gasoline-filled lake. Two very different parties happening simultaneously. What a fascinating conundrum for future explorers. The existence of such a subsurface ocean is supported by observations from the Cassini mission, which detected variations in Titan's rotation that are best explained by a liquid layer beneath its surface. This sloshing effect hints at a dynamic interior. If this deep ocean exists, it would be protected from the harsh radiation and extreme temperatures of space, much like Europa's and Enceladus's oceans. The big difference, of course, would be the interaction between this deep ocean and the bizarre chemistry happening on the surface. Imagine for a moment methane raining down, seeping through cracks in the ice, and eventually reaching the water ocean below. What kind of chemical reactions might occur at that interface? It's a tantalizing thought, a cosmic melting pot of possibility. This truly pushes the boundaries of your imagination, doesn't it? Now let's take a dramatic turn and head back inwards towards Jupiter, but this time to its innermost large moon, Io. Prepare for a shock, because Io is nothing like the serene, icy worlds we've been discussing. Io is, quite frankly, a volcanic hellscape. It is the most volcanically active body in the entire solar system, constantly erupting with plumes of sulfur and sulfur dioxide reaching hundreds of kilometers into space. Imagine Mount Vesuvius going off every single day, but multiplied by 1,000 across an entire moon. It's a fiery, dramatic spectacle, and frankly, a bit unsettling. A mainstream historical fact is that the Voyager 1 spacecraft, during its flyby in 1979, provided the first evidence of active volcanism on Io, completely redefining our understanding of geological activity beyond Earth. Before that, scientists mostly expected cold, dead worlds in the outer solar system. Talk about a surprise. The reason for Io's extreme volcanism lies in its intense tidal heating from Jupiter. Io is caught in a powerful gravitational tug-of-war between Jupiter and its other large moons, Europa and Ganymede. This constant gravitational squeezing and stretching generates immense friction and heat within Io's interior, melting its rocky mantle and leading to continuous eruptions. It's like endlessly bending a paperclip back and forth until it gets hot. Except here, the paperclip is a moon, and the heat is enough to make it continuously erupt. You wouldn't want to vacation there unless your idea of fun involves dodging molten sulfur and breathing in toxic fumes. Forget postcards, you'd be sending out hazard warnings. Given its volcanic nature, Io is almost certainly not a candidate for life as we know it. The surface is constantly being resurfaced by lava flows, and the extreme radiation from Jupiter, combined with the volcanic gases, creates an incredibly hostile environment. It's a bit like trying to find life on the inside of an active blast furnace. Not impossible if you're a truly extremophile, but definitely a long shot. However, Io's intense geological activity provides invaluable insights into planetary formation and evolution. It shows us the sheer power of tidal forces and how they can shape celestial bodies in ways we might never have imagined. One quirky tidbit about Io is that its surface is constantly changing, with new volcanic features appearing and old ones disappearing in a matter of months. Maps of Io quickly obsolete. It's like trying to keep up with fashion trends in a whirlwind. Can you imagine updating your GPS every few days just to navigate a moon? Despite the unlikeliness of finding life on Io itself, the energy and chemistry it generates might have implications for the surrounding Jovian system. For instance, the volcanic plumes contribute material to Jupiter's magnetosphere, potentially influencing other moons. Historians still argue whether the discovery of Io's volcanism was more important for understanding the mechanics of tidal heating or for simply shattering preconceived notions about moon geology. Either way, it fundamentally changed our view of what a moon could be. It serves as a powerful reminder that the universe is full of surprises, and our understanding of what's normal is constantly being challenged.
From the fiery chaos of Io, we now zoom out to the furthest major moon in the Jovian system that still holds a gravitational thrall over our curiosity, even if it's not a primary candidate for life itself: Triton. This fascinating moon orbits Neptune, and it's a true oddity in our solar system. The most striking thing about Triton is its retrograde orbit. It orbits Neptune in the opposite direction to Neptune's own rotation. This is highly unusual for a large moon and strongly suggests that Triton wasn't formed alongside Neptune, but was captured by its gravity much later. Imagine a planet walking its dog, but the dog is stubbornly walking backward on the leash. It's a cosmic anomaly, a rogue moon pulled into Neptune's embrace. A mainstream historical fact is that Triton was visited by only one spacecraft, Voyager 2, in 1989, which provided our only close-up images and data of this enigmatic world. Can you picture that solitary probe venturing into the cold, distant unknown, capturing these unique first glimpses? Triton is a cryovolcanic world, meaning it has volcanoes that erupt not with molten rock, but with volatiles like liquid nitrogen, ammonia, or water. Voyager 2 observed active geysers on Triton, spewing plumes of nitrogen ice particles and dark organic material several kilometers into space. These plumes create dark streaks on Triton's surface, carried by winds in its extremely tenuous atmosphere. It's like a cosmic snow globe, except the snow is made of frozen nitrogen, and the flakes are being actively shot out by underground forces. The surface itself is a surreal landscape of nitrogen ice plains, cantaloupe-like terrain, and what appear to be frozen lakes. The temperatures are incredibly low, around -235 degrees Celsius, -391 Fahrenheit, making it one of the coldest places in the solar system. You wouldn't want to forget your winter coat there, believe me. The active cryovolcanicism on Triton indicates that despite its extreme cold, there's internal heating at play, likely from tidal forces as it orbits Neptune, though perhaps not enough to sustain a global liquid water ocean like on Europa or Enceladus. However, the presence of internal heat and the activity of nitrogen geysers does hint at a dynamic interior. Could there be pockets of liquid water, perhaps salty brines, deep beneath the surface, warmed by this internal activity? It's not as strong a case as for Europa or Enceladus, but it's not entirely out of the question for extremophile life should it exist in such harsh conditions. One quirky tidbit about Triton is that it's slowly spiraling inward towards Neptune and is predicted to eventually be torn apart by Neptune's gravity in about 3.6 billion years, forming a new ring system. So, enjoy it while it lasts. You're getting a preview of a cosmic demolition job. Historians still argue whether Triton's retrograde orbit or its cryovolcanic activity was the more unexpected discovery from the Voyager 2 flyby. Both shattered prevailing notions about moon formation and the types of geological processes that could occur on icy worlds so far from the Sun. Triton reminds us that even at the very edges of our solar system, beyond the gas giants, there are still worlds that harbor internal activity and surprise. It's a testament to the incredible diversity of celestial bodies, proving that the universe consistently outdoes our wildest imaginings. What other cosmic oddities do you think are lurking out there? Now, let's pivot back to Jupiter's largest moon, the grandest of them all, Ganymede. If moons were royalty, Ganymede would be the undisputed king. It's not just the largest moon in the solar system, it's bigger than the planet Mercury and even dwarf planet Pluto. This sheer size alone makes it a compelling world. But Ganymede has another unique feature that sets it apart. It possesses its own intrinsic magnetic field. This is incredibly rare for a moon, typically a characteristic of planets with active molten cores generating a dynamo effect. It's like finding a small car that somehow generates its own entire power grid. The presence of a magnetic field strongly suggests that Ganymede has a liquid metallic core, possibly composed of iron, similar to Earth. This internal heat source, combined with tidal heating from Jupiter, could be sufficient to maintain multiple layers of liquid water oceans sandwiched between layers of ice. Scientists theorize that Ganymede might have a club sandwich structure of ice and water, with different depths and salinities. It's an astrobiologist's dream, offering multiple potential habitats protected by thick icy shells.
The possibility of multiple subsurface oceans within Ganymede, each potentially interacting with different rock layers, makes it incredibly intriguing for the search for life. You're not just looking for one hidden pool, but possibly a multi-story aquatic apartment complex, each floor offering slightly different conditions. The presence of its own magnetic field is also significant, as it creates a mini magnetosphere around the moon, partially shielding its surface from Jupiter's intense radiation belt. While this shield might not extend deep enough to protect the oceans entirely, it certainly influences the chemistry occurring on and near the surface, which could, in turn, affect the ocean below. It's like finding a small car that generates its own power grid, a truly unique situation. A quirky tidbit: Ganymede is so large that if it orbited the Sun instead of Jupiter, it would actually be classified as a planet. It's truly a planetary-sized moon, holding its own against the smaller planets in our solar system. Doesn't that make you wonder about the cosmic classifications we've made? Scientists are particularly interested in the interface between Ganymede's rocky core and its innermost ocean. Similar to Europa and Enceladus, if this ocean is in contact with rock, it opens up the possibility of hydrothermal activity, providing the heat and chemical nutrients that could support life. While Europa might be the frontrunner for current habitability due to its younger, more dynamic ice shell and greater tidal heating, Ganymede's sheer volume of water and the long-term stability offered by its layered structure make it a strong contender for past or present life. Historians still argue whether the discovery of Ganymede's magnetic field was more pivotal than the evidence for its layered oceans in shifting our focus for astrobiological exploration. Both were monumental. Next up, we have Callisto, another of Jupiter's Galilean moons. Callisto is the furthest of the four major moons from Jupiter, and this distance has played a crucial role in its geological history. Unlike its siblings Europa and Io, which are constantly being kneaded by Jupiter's immense gravity, Callisto experiences much weaker tidal forces. The result? Callisto is a largely inactive ancient world, its surface heavily pockmarked with craters, preserving a record of impacts stretching back billions of years, almost like a cosmic punching bag that's never been quite cleaned up.
It's the equivalent of finding a perfectly preserved fossilized forest, but on a moon. A mainstream historical fact is that Callisto's heavily cratered surface made it clear early on that it had undergone very little geological resurfacing, providing a stark contrast to its more active neighbors. You can almost see the history etched onto its very face. Despite its outwardly calm, ancient appearance, Callisto still holds a secret. Evidence suggests it, too, might harbor a subsurface liquid water ocean. While the tidal heating isn't as strong on Europa, models indicate that a layer of salty water could exist roughly 200 to 300 kilometers beneath its icy crust. This ocean would be kept liquid by a combination of a small amount of residual internal heat from its formation and the inclusion of antifreeze-like salts. It's like finding a perfectly still, deep lake under an ancient, undisturbed wilderness. Calm, but potentially full of unseen wonders. Could you imagine the tranquility of that hidden sea? However, a key difference with Callisto's potential ocean is that it's likely not in direct contact with a rocky core. Instead, it's believed to be sandwiched between two layers of ice, like the cream filling in an Oreo cookie, but a very, very thick one. This means there would be no hydrothermal vents providing energy and chemicals from rock-water interactions, which are considered crucial for life as we know it. So, while Callisto might have water, the conditions for life might be far less favorable compared to Europa or Enceladus. It's a bit like having a perfectly good swimming pool, but without any snacks or entertainment nearby. Still, it's a pool, right? Nevertheless, the mere presence of liquid water on such an ancient, seemingly inert body expands our understanding of where water can persist in the solar system. It suggests that once a moon has enough water, it can hold onto it in liquid form for incredibly long periods, even without strong tidal forces. One quirky tidbit about Callisto is that its heavily cratered surface makes it look remarkably similar to our own moon from a distance, albeit much larger and icier. Historians still argue whether Callisto's ancient surface offers more insights into the early bombardment period of the solar system or into the long-term stability of subsurface oceans. In either case, it's a window into the deep past. It truly makes you ponder the immense timescales in cosmic evolution.
So, while Callisto's ocean might not be as dynamic or as promising for life as those on Europa or Enceladus, its existence underscores a profound point. Liquid water, the essential ingredient for life, seems to be far more common in our solar system than we once imagined. It's like realizing that instead of just one hidden spring, your backyard is dotted with several, each with its own unique characteristics. Even on a moon that appears geologically inert on the surface, mysteries can lie deep beneath the cold exterior. It truly makes you wonder about all the other hidden pockets of liquid out there, doesn't it? Now, let's take a quick interstellar hop from Jupiter's system to Saturn's, but bypass the obvious stars like Enceladus and Titan for a moment, and instead turn our attention to a truly iconic, if scientifically less promising, moon, Mimas. You might not know Mimas by name, but you almost certainly know it by sight. It's the moon that looks uncannily like the Death Star from Star Wars. That giant, prominent crater, Herschel, covers almost a third of the moon's diameter, making it one of the largest impact craters relative to the size of its parent body in the entire solar system. It's a bit like someone punched a massive hole right through the middle of a golf ball. A mainstream historical fact is that the resemblance to the Death Star was immediately noted upon its imaging by the Voyager missions in the late 1970s and early 1980s, forever cementing its pop culture status. You probably instantly recognized it, didn't you? Mimas is relatively small, only about 396 kilometers, 246 miles in diameter, and its density suggests it's primarily composed of water ice with only a small amount of rock.
Despite its ice-rich composition, Mimas isn't thought to harbor a global subsurface ocean. Its proximity to Saturn means it experiences significant tidal forces, but these forces seem to be mostly responsible for keeping its interior relatively warm, preventing it from completely freezing solid rather than creating a liquid ocean. It's like a perpetually slightly defrosted ice cube rather than a glass of water. However, there's a quirky tidbit about Mimas that is scientifically fascinating: its surprising and significant influence on Saturn's rings. Mimas is in what's called an orbital resonance with particles in Saturn's Cassini division, a prominent gap in the rings. Its gravity regularly nudges these particles, clearing them out and creating that distinct gap. It's a bit like a cosmic sheepdog herding ring particles into neat divisions. So, while Mimas itself isn't a likely candidate for life, its orbital dance is directly responsible for one of the most stunning features of our solar system. Historians still argue whether Mimas's role in shaping Saturn's rings or its distinctive Death Star appearance made it more famous in popular culture. Both certainly contributed to its enduring legacy. From Mimas, we move on to another of Saturn's moons, Rhea. Rhea is the second largest of Saturn's moons, after Titan, and it's a relatively airless, icy body. Its surface is heavily cratered, indicating an old, stable crust with little geological activity, similar in some ways to Callisto. Imagine a giant, well-used dartboard, constantly getting new marks, but never quite getting smoothed over. Does that conjure a clear picture for you? One of the more intriguing, if tenuous, discoveries about Rhea is the possible detection of a faint ring system around it. In 2008, data from the Cassini spacecraft suggested the presence of dust and debris orbiting Rhea, potentially forming a very thin ring. If confirmed, Rhea would be the first moon known to have its own rings. This discovery is still debated and requires further confirmation, but it paints an interesting picture of how even relatively small bodies can influence their immediate surroundings. It's like finding a tiny, forgotten halo around a somewhat plain stone. While Rhea's surface is cold and inactive, some models suggest that it could have a very deep, long-lived subsurface ocean, perhaps hundreds of kilometers beneath its icy crust, maintained by the decay of radioactive elements within its rocky core. This idea is less robust than for Europa or Enceladus, but it cannot be entirely discounted. The potential ocean, if it exists, would likely be far removed from any rock-water interactions, making it less likely to host life as we know it. Still, the mere potential for liquid water hidden within such a seemingly inert body underscores the continuing surprises our solar system holds. Historians still argue whether the initial evidence for Rhea's ring system or its potential deep ocean was the more significant discovery for planetary science. Both provide valuable pieces of the puzzle. It truly highlights how much there is left to uncover, even in our own cosmic neighborhood.
From Rhea's potential deep, dark ocean, we glide further into the Saturnian system, to a moon that shows a bit more geological flair than its heavily cratered neighbors, Dione. Dione is an icy moon, but unlike Callisto or Rhea, it displays clear evidence of past geological activity, particularly in its distinctive wispy terrains, which are actually bright icy cliffs and canyons that stretch across its trailing hemisphere. Imagine giant luminous scratches across a bowling ball created by some long ago cosmic accident. These features suggest internal processes that fractured and resurfaced parts of the moon. A mainstream historical fact is that the Voyager missions first captured these wispy features, leading scientists to realize that even relatively small icy moons could be geologically active. It truly makes you wonder about the forces that shaped this distant world. Dione's surface is a mix of heavily cratered terrain and more lightly cratered, smoother plains, indicating episodes of resurfacing in its past. The prominent chasmata, or canyons, are thought to be tectonic in origin, perhaps formed by the expansion and contraction of the Moon's ice shell. While Dione isn't currently known to have active plumes like Enceladus, the evidence of past activity hints at a more dynamic interior than its looks might initially suggest. This dynamic past is crucial for understanding its potential to harbor a subsurface ocean. What other ancient secrets might it hold? Like many icy moons, Dione is believed to possess a subsurface ocean, specifically a global liquid water ocean situated deep beneath its icy crust. This ocean, likely maintained by tidal heating from Saturn, would be considerably deeper than Enceladus's ocean, perhaps around 100 kilometers, 60 miles below the surface. However, unlike Enceladus's ocean, Dione's is not thought to be in direct contact with a rocky core. Instead, it's likely sandwiched between two layers of ice, similar to the proposed scenario for Callisto. This means the absence of rock-water interactions would likely limit the chemical energy sources needed for life as we know it. It's like having a grand swimming pool, but the snack bar is permanently closed. Still, a pool's a pool, right? Despite this, the sheer volume of water, protected from the harsh surface environment, makes Dione another contender for long-term liquid water presence. While not a prime target for current life, it could offer insights into the long-term evolution of icy worlds and the persistence of liquid water under less dynamic conditions. One quirky tidbit about Dione is that it's often described as a half-and-half moon, with one hemisphere heavily cratered and the other displaying those distinctive bright fractured terrains. It's like someone got bored decorating halfway through. Historians still argue whether the presence of Dione's ancient fractured terrain or the potential for a very deep isolated ocean is more significant for our understanding of icy moon evolution. Both provide valuable pieces of the puzzle. What do you think is more compelling? Now, let's swing over to Uranus's system, a truly bizarre collection of moons, and focus on one of the strangest, Miranda. Miranda is the smallest and innermost of Uranus's 5 major moons, and it looks like a celestial Frankenstein's monster, a bizarre mishmash of different terrains. Its surface is a jumble of ancient, heavily cratered regions alongside strange chevron-shaped features called coronae or ovoids, which are enormous, relatively smooth oval or trapezoidal regions bordered by faults. Imagine a marble that someone tried to assemble from several different oddly shaped pieces, then dropped on the floor. It truly is a chaotic spectacle, isn't it? This chaotic, jumbled appearance suggests an incredibly violent past. One theory is that Miranda was shattered by a massive impact sometime in its history, and then the pieces reaccreted or came back together in a haphazard fashion. Another, more widely accepted theory posits that the coronae are evidence of slow, sluggish convection in Miranda's interior, causing warm ice to rise and cold ice to sink, leading to resurfacing. This would indicate internal activity, even if it's not enough to maintain a global liquid ocean today. It's like watching molasses slowly bubble, but on a moon-sized scale. Miranda's extreme axial tilt, Uranus itself is tilted on its side, and its moons generally follow suit, means it experiences extreme seasonal variations, with parts of the moon plunged into continuous darkness for decades. This, combined with its small size and likely limited internal heat, makes a subsurface liquid water ocean unlikely in the present day. However, the moon's strange features continue to puzzle scientists and hint at periods of past internal activity that could have transiently supported liquid water. One quirky tidbit about Miranda is that it's often described as a half-and-half moon, with one hemisphere heavily cratered and the other displaying those distinctive bright fractured terrains. It's like someone got bored decorating halfway through. Historians still argue whether the presence of Dion's ancient fractured terrain or the potential for a very deep isolated ocean is more significant for our understanding of icy moon evolution. Both provide valuable pieces of the puzzle. What do you think is more compelling? Now, let's swing over to Uranus's system, a truly bizarre collection of moons, and focus on one of the strangest, Miranda. Miranda is the smallest and innermost of Uranus's 5 major moons, and it looks like a celestial Frankenstein's monster, a bizarre mishmash of different terrains. Its surface is a jumble of ancient, heavily cratered regions alongside strange chevron-shaped features called coronae or ovoids, which are enormous, relatively smooth oval or trapezoidal regions bordered by faults. Imagine a marble that someone tried to assemble from several different oddly shaped pieces, then dropped on the floor. It truly is a chaotic spectacle, isn't it? This chaotic, jumbled appearance suggests an incredibly violent past. One theory is that Miranda was shattered by a massive impact sometime in its history, and then the pieces reaccreted or came back together in a haphazard fashion. Another, more widely accepted theory posits that the coronae are evidence of slow, sluggish convection in Miranda's interior, causing warm ice to rise and cold ice to sink, leading to resurfacing. This would indicate internal activity, even if it's not enough to maintain a global liquid ocean today. It's like watching molasses slowly bubble, but on a moon-sized scale. Miranda's extreme axial tilt, Uranus itself is tilted on its side, and its moons generally follow suit, means it experiences extreme seasonal variations, with parts of the moon plunged into continuous darkness for decades. This, combined with its small size and likely limited internal heat, makes a subsurface liquid water ocean unlikely in the present day. However, the moon's strange features continue to puzzle scientists and hint at periods of past internal activity that could have transiently supported liquid water. One quirky tidbit about Miranda is that its largest canyon, Verona Rupus, is thought to be the tallest cliff in the solar system, plunging some 20 kilometers, 12 miles deep. If you jumped off it, you'd have a 12-minute fall. Not that I recommend it, of course. The unusual appearance of Miranda remains one of the great mysteries of the outer solar system. Historians still argue whether Miranda's unique surface features are best explained by catastrophic impacts or by more gradual internal convection. Either way, it highlights how much we still have to learn about the diverse ways moons can evolve. It's a testament to the idea that even the smallest, most seemingly insignificant bodies can hold profound geological secrets.
From the bizarre geological patchwork of Miranda, we move to a moon that, at first glance, seems to be the very antithesis of active, Umbriel. This is another of Uranus's major moons, and it's remarkably dark and featureless. Imagine a perfectly smooth charcoal gray cue ball, but one that's been in space for billions of years without much happening to it. Umbriel has one of the darkest surfaces of any moon in the solar system, reflecting very little sunlight. This suggests that its surface is coated in a layer of dark, primitive material, perhaps organic compounds or carbonaceous chondrite-like material, and that it has undergone very little geological activity since its formation. It's like finding a dusty, undisturbed attic that hasn't been touched in millennia. A mainstream historical fact is that Umbriel, along with Uranus's other moons, was first observed by William Herschel in the late 18th century. But its true dark nature only became apparent with the Voyager 2 flyby. Can you picture that deep, untouched darkness?
The most prominent feature on Umbriel is the oddly bright, ring-like formation near its equator called Wunda crater. This bright ring contrasts sharply with the Moon's otherwise dark surface, but it's an isolated feature on an otherwise remarkably uniform world. The lack of varied terrain, fresh impact craters, or evidence of resurfacing points to a cold, inert interior. Given its dark, ancient surface and apparent lack of geological activity, Umbriel is generally not considered a prime candidate for harboring a subsurface liquid water ocean. The internal heating mechanisms that could melt ice are likely very weak, if present at all. Any water within Umbriel is probably frozen solid, forming a thick, rigid ice mantle down to its small, rocky core. It's a bit like a giant, solid ice cube that's been left in the freezer for eons. However, the exact composition of its dark surface material remains a subject of scientific debate. One quirky tidbit about Umbriel is that its dark surface might be a result of space weathering over billions of years, or perhaps it accreted from darker material than its brighter Uranian siblings. Historians still argue whether Umbriel's uniform darkness tells us more about the composition of the early solar nebula or the long-term effects of space radiation. Both are intriguing possibilities, don't you think? Now, let's brighten things up a bit with Ariel, another of Uranus's major moons, and what a difference a moon makes. Ariel is the brightest of Uranus's moons and shows clear evidence of relatively recent geological activity. Its surface is a mix of heavily cratered terrain and extensive networks of valleys and ridges, known as graben systems. These graben are thought to be caused by tectonic forces, where the moon's crust has pulled apart, creating sunken valleys. Imagine pulling apart a piece of fabric and seeing the threads stretch and create gaps. A mainstream historical fact, Ariel's bright surface and graben features were a surprise during the Voyager 2 flyby, indicating that even in the frigid outer solar system, moons could still experience periods of internal heating and resurfacing. You can almost feel the ground shifting beneath you, can't you? The presence of these graben systems suggests that Ariel has undergone periods of expansion and contraction, which typically requires a source of internal heat. This heat could have come from tidal forces from Uranus, or perhaps from the decay of radioactive elements within its core. This internal activity makes Ariel a more plausible candidate for a past or even present subsurface liquid water ocean compared to Umbriel. If an ocean existed, even transiently, it would have been capable of driving the geological processes that shaped its surface. It's like a slightly rusty old engine that still manages to sputter to life now and then. One quirky tidbit about Ariel is that its surface shows what appear to be cryovolcanic flows, where very cold, slushy ice has erupted onto the surface, smoothing out older craters. It's like a slow-motion, extremely chilly lava lamp. Historians still argue whether the evidence for tectonic activity or cryovolcanicism on Ariel is more compelling for understanding the extent of internal heating on these distant moons. Both are fascinating avenues of inquiry, don't you think? Now, let's brighten things up a bit with Ariel, another of Uranus's major moons, and what a difference a moon makes. Ariel is the brightest of Uranus's moons and shows clear evidence of relatively recent geological activity. Its surface is a mix of heavily cratered terrain and extensive networks of valleys and ridges, known as graben systems. These graben are thought to be caused by tectonic forces, where the moon's crust has pulled apart, creating sunken valleys. Imagine pulling apart a piece of fabric and seeing the threads stretch and create gaps.
A mainstream historical fact, Ariel's bright surface and graben features were a surprise during the Voyager 2 flyby, indicating that even in the frigid outer solar system, moons could still experience periods of internal heating and resurfacing. You can almost feel the ground shifting beneath you, can't you? The presence of these graben systems suggests that Ariel has undergone periods of expansion and contraction, which typically requires a source of internal heat. This heat could have come from tidal forces from Uranus, or perhaps from the decay of radioactive elements within its core. This internal activity makes Ariel a more plausible candidate for a past or even present subsurface liquid water ocean compared to Umbriel. If an ocean existed, even transiently, it would have been capable of driving the geological processes that shaped its surface. It's like a slightly rusty old engine that still manages to sputter to life now and then. While a definitively confirmed ocean on Ariel is not yet on the books, the geological evidence strongly implies periods where internal heat was sufficient to melt ice or at least become malleable. Such an ocean, if present, would likely be situated deep beneath the surface, protected by a thick ice shell. The conditions for life would depend on whether this water interacted with a rocky core to provide chemical energy, similar to Europa or Enceladus, though likely to a lesser extent. One quirky tidbit about Ariel is that its surface shows what appear to be cryovolcanic flows, where very cold, slushy ice has erupted onto the surface, smoothing out older craters. It's like a slow-motion, extremely chilly lava lamp. Historians still argue whether the evidence for tectonic activity or cryovolcanicism on Ariel is more compelling for understanding the extent of internal heating on these distant moons. Both are fascinating avenues of inquiry. The diverse geological histories of Uranus's moons, from the dead calm of Umbriel to the active or once active terrains of Miranda, highlight the varied paths that icy worlds can take in their evolution. They serve as a reminder that even in the distant reaches of our solar system, beyond the warmer, more familiar inner planets, there's a surprising amount of dynamism and potential, even if it's not always in the way we expect.
The journey through the solar system's icy moons, from the dramatic plumes of Enceladus to the subtle clues of subsurface oceans on moons like Dione and Ariel, consistently brings us back to one fundamental question. How do we know these oceans exist, and how do we eventually find out if they harbor life? This brings us to the exciting realm of future missions and the innovative ways scientists are planning to explore these enigmatic worlds. It's like having a treasure map, and now you're finally getting the tools to start digging. A mainstream historical fact is that the success of the Voyager and Cassini missions, specifically their extended lifespans and close-up observations, truly paved the way for the ambitious missions being planned today, proving that long-duration, deep space exploration is not just feasible, but incredibly rewarding. Can you feel that sense of anticipation building? For Europa, the next big step is the Europa Clipper mission, which we touched upon earlier. This spacecraft isn't designed to land, at least not initially. Instead, it will perform dozens of close flybys of Europa, dipping into the intense radiation belts around Jupiter to gather data. Its sophisticated instruments will include cameras to map the surface in unprecedented detail, spectrometers to analyze the composition of the ice and any plumes, and radar to peer through the ice shell and determine the thickness and characteristics of the subsurface ocean. Think of it as a cosmic ultrasound designed to reveal what's hiding beneath the moon's frozen skin. The goal is to confirm the ocean's existence and characterize its potential habitability. It's a bit like sending a highly advanced drone to scout out a potential secret base before sending in the ground troops. What an ingenious approach to reconnaissance!
Following Europa Clipper, there's a strong push for a Europa lander mission, which would, as its name suggests, land on the Moon's surface. The primary goal of a lander would be to directly search for signs of life, perhaps by analyzing samples of the surface ice that might contain traces of ocean water, or by deploying a small drill to access material just beneath the crust. Imagine a robotic explorer carefully sifting through icy dust, searching for microscopic evidence of alien biology. This would be a monumental undertaking given the extreme environment and the need to maintain pristine scientific conditions to avoid contaminating the Moon with Earth microbes. You wouldn't want to accidentally introduce alien flu, would you? For Enceladus, while no definitive lander mission is currently funded, the scientific community is buzzing with ideas for future exploration. Given its active plumes, a favored concept is a plume surfer mission, where a spacecraft would literally fly through the plumes, collecting samples of the ejected material. This would offer a direct way to analyze the ocean's chemistry without having to drill through ice, potentially revealing the presence of complex organic molecules or even direct biosignatures. It's like having the Moon send you a postal package filled with its most valuable secrets, no picking of locks required. One quirky tidbit about future plume missions, engineers are considering using aerocapture technology, where the spacecraft would use a planet's atmosphere to slow down and enter orbit, saving vast amounts of fuel. Titan also has incredibly exciting future missions on the horizon. The most prominent is Dragonfly, a NASA mission that will send a rotorcraft lander, essentially a drone, to Titan. Dragonfly will hop between different locations on Titan's surface, exploring various environments, including dunes, impact craters, and the shores of its methane lakes. This will allow scientists to study Titan's complex organic chemistry in situ, search for evidence of past or present liquid water, and understand the processes that shape this unique world. Imagine a giant nuclear-powered bumblebee buzzing across an alien landscape, meticulously sampling everything it can. A mainstream historical fact here, Dragonfly represents a truly revolutionary approach to planetary exploration, leveraging aerial mobility to explore a diverse range of terrains, a concept that was almost unthinkable just a few decades ago. It truly redefines what a space mission can be, doesn't it? Dragonfly won't be explicitly searching for life in the methane lakes, but it will be looking for the complex organic chemistry that could serve as precursors to life, or even for signs of exotic life that uses methane as a solvent. Its ability to move between sites will provide a wealth of information about Titan's dynamic environment. Historians still argue whether the development of autonomous aerial vehicles for planetary exploration or the pursuit of exotic life on Titan represents the greater leap in astrobiological ambition. Both are certainly pushing the boundaries. For Ganymede, the European Space Agency, ESA, is leading the Jupiter Icy Moons Explorer, set to launch in 2023. JUICE will conduct detailed observations of Jupiter and its 3 large icy moons, Ganymede, Callisto, and Europa, with a particular focus on Ganymede. It will be the first spacecraft to orbit an outer planet moon, spending 9 months orbiting Ganymede. This prolonged study will allow JUICE to precisely map Ganymede's magnetic field, investigate its complex internal structure, and search for its suspected subsurface ocean. It's like finally getting to move into the biggest house on the block and meticulously inspecting every room.
The data from JUICE, combined with insights from Europa Clipper, will revolutionize our understanding of the Galilean moons and their potential for habitability. JUICE's focus on Ganymede specifically will provide unprecedented details about its intrinsic magnetic field and the layered structure of its interior, helping us to unravel the complex interplay between its core, its presumed oceans, and its unique magnetic bubble. It's like finally getting to look at the X-ray of a complex geological sandwich, seeing all the layers and what they're made of. Can you imagine the incredible detail these missions will reveal? While these missions are incredibly ambitious and expensive, the potential scientific payoff, the discovery of life beyond Earth, is considered by many to be one of the most profound achievements humanity could ever make. The very act of designing these missions pushes the boundaries of engineering and robotics, developing technologies that often find applications back here on Earth. So even if we don't find alien squids, the journey itself is incredibly valuable. A quirky tidbit? Some of the sensors designed for these deep space missions, needing to operate in extreme cold and radiation, are so sensitive they could detect a single molecule of a specific substance from miles away. Imagine a bloodhound that can sniff out a single sugar cube in a football stadium. That's some serious sniffing power. Beyond the specific missions to individual moons, there's also the ongoing development of more general technologies that could unlock the secrets of these icy worlds. This includes advanced drilling techniques for penetrating thick ice shells, autonomous underwater vehicles, AUVs, that could explore subsurface oceans, and highly sensitive biosignature detectors that can distinguish between geological processes and actual signs of life. It's like preparing an entire toolkit filled with specialized instruments for whatever mysteries we might encounter. The challenges are immense, of course. The vast distances involved mean communication delays and limited data rates. The extreme temperatures and radiation environments require incredibly robust and resilient spacecraft. And the sheer unknown. What if the oceans are too salty, or too acidic, or too something else entirely? Means every mission is a leap of faith into the cosmic unknown. Historians still argue whether the technological challenges of deep space missions or the ethical considerations of potentially discovering alien life pose the greater hurdle. Both are significant. Now, let's turn our attention to the actual act of defining what makes a world habitable, especially in the context of these fascinating moons. It's not as simple as just water equals life. While liquid water is indeed considered the most crucial ingredient for life as we know it, several other factors play equally important roles. Think of it like baking a cake. You need flour, but you also need sugar, eggs, and heat in the right proportions. First and foremost is an energy source. Life needs energy to grow, reproduce, and maintain itself. On Earth, the primary energy source is the sun through photosynthesis. But as we've seen with Europa and Enceladus, life can also thrive on chemical energy, powered by hydrothermal vents. This concept of chemosynthesis is a game changer for astrobiology, vastly expanding the potential locations for life beyond the reach of sunlight. It's like realizing that instead of just eating food cooked on a stove, you can also enjoy a meal prepared over a campfire. Doesn't that expand your idea of where life could exist? Second, life requires a suite of essential chemical building blocks. These typically include carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, often remembered by the acronym CHOPS. These elements are the fundamental ingredients for amino acids, proteins, DNA, and all the complex organic molecules that make up living organisms. Fortunately, these elements are relatively common throughout the universe and have been detected on many of the moons we've discussed, particularly in the plumes of Enceladus and the atmosphere of Titan.
It's like finding all the basic Lego bricks ready to be assembled into something intricate. Third, a stable environment is generally preferred. While extremophiles on Earth show incredible resilience, prolonged periods of extreme radiation, rapid temperature swings, or violent geological upheaval would make it incredibly difficult for life to emerge and evolve. This is where the subsurface oceans of Europa and Enceladus shine. The thick ice shells provide a stable, protected environment, shielding any potential life from the harsh surface conditions and radiation. It's like having a perfectly climate-controlled underground bunker, safe from the storms above.
So, while the surface of Europa might be bombarded by Jupiter's fearsome radiation belts, deep within its ocean, any potential life would be perfectly insulated. It's the ultimate VIP lounge, protected from the cosmic paparazzi. This stability is a key factor in habitability, suggesting that even if a world has the right ingredients, extreme fluctuations might prevent life from taking hold or persisting for long. You can truly appreciate the importance of that hidden sanctuary, can't you? Fourth, the presence of solvents other than water is a fascinating, if highly speculative, avenue for defining habitability. While water is undoubtedly the universal solvent for Earth life, scientists are considering whether other liquids, like the methane and ethane on Titan, could support radically different forms of life. This requires pushing our scientific imaginations to their limits, envisioning biochemistry that operates under vastly different conditions. It's like trying to imagine a car that runs on sunshine instead of gasoline. Theoretically possible, but fundamentally different in its mechanics. This concept is often referred to as alternative biochemistries. The ongoing search for extraterrestrial life is not just about finding another Earth. It's about broadening our understanding of what life can be. The moons of our solar system, with their unique chemistries and extreme environments, are pushing the boundaries of that definition. They are cosmic laboratories testing the very limits of habitability. A mainstream historical fact is that the Miller-Urey experiment in the 1950s, which simulated early Earth conditions and produced amino acids, demonstrated that the basic building blocks of life could form spontaneously under certain circumstances. This early work laid a foundational stone for understanding how life might originate even on alien worlds. Doesn't that make you feel a connection to those pioneering scientists? The last crucial element, and perhaps the most difficult to ascertain remotely, is time. Life needs sufficient time to emerge, evolve, and diversify. The oceans of Europa and Enceladus are thought to have existed for billions of years, providing ample time for any nascent life to develop. Titan's methane cycle has also been active for a very long time, offering a prolonged period for its unique chemistry to unfold. It's like tending a garden. You can plant the seeds, but you need patience for them to grow into something beautiful. The implications of discovering life on one of these moons would be monumental, revolutionizing not only biology, but also philosophy and our place in the universe. It would tell us that life isn't a unique phenomenon to Earth, but perhaps a common occurrence wherever the conditions are right. It's like realizing your hometown isn't the only place with people. The whole world is full of them. One quirky tidbit about the search for life: some scientists are developing extremely sensitive sniffers for specific gases, like phosphine, which on Earth is often associated with biological activity and might serve as a biosignature on other worlds. So, in the future, we might literally be sniffing out aliens. You wouldn't want to leave your cosmic air freshener at home.
Historians still argue whether the most profound impact of discovering extraterrestrial life would be scientific or philosophical. Both are undeniably significant. Such a discovery would challenge anthropocentric views and force us to reevaluate our understanding of the cosmos and our role within it. It would be a paradigm shift unlike any other in human history. Now, as our journey nears its end, let's take a moment to reflect on the sheer audacity of these moons and their potential. We've crisscrossed the solar system from the fiery hell of Io to the icy depths of Europa, from the methane lakes of Titan to the ancient quiet of Callisto. Each moon, in its own peculiar way, has offered a glimpse into the incredible diversity of worlds that orbit our planets. They are not just silent companions, they are active, dynamic bodies, each with its own story to tell and perhaps its own life to harbor. The ongoing search for life on these fascinating moons is one of the most exciting frontiers in modern science. It's a quest that combines cutting-edge technology with deep scientific curiosity, pushing the boundaries of what we know about the universe and our place within it. The next few decades, with missions like Europa Clipper, Dragonfly, and JUICE, promise to be a golden age of icy moon exploration. We are on the cusp of truly answering questions that humanity has pondered for millennia. Are we alone? And if not, where are they? One quirky tidbit about the search for life: some scientists are developing extremely sensitive sniffers for specific gases, like phosphine, which on Earth is often associated with biological activity and might serve as a biosignature on other worlds. So, in the future, we might literally be sniffing out aliens. You wouldn't want to leave your cosmic air freshener at home. Historians still argue whether the most profound impact of discovering extraterrestrial life would be scientific or philosophical. Both are undeniably significant. Such a discovery would challenge anthropocentric views and force us to reevaluate our understanding of the cosmos and our role within it. It would be a paradigm shift unlike any other in human history. Now, as our journey nears its end, let's take a moment to reflect on the sheer audacity of these moons and their potential. We've crisscrossed the solar system from the fiery hell of Io to the icy depths of Europa, from the methane lakes of Titan to the ancient quiet of Callisto. Each moon, in its own peculiar way, has offered a glimpse into the incredible diversity of worlds that orbit our planets. They are not just silent companions, they are active, dynamic bodies, each with its own story to tell and, perhaps, its own life to harbor. The ongoing search for life on these fascinating moons is one of the most exciting frontiers in modern science. It's a quest that combines cutting-edge technology with deep scientific curiosity, pushing the boundaries of what we know about the universe and our place within it. The next few decades, with missions like Europa Clipper, Dragonfly, and JUICE, promise to be a golden age of icy moon exploration. We are on the cusp of truly answering questions that humanity has pondered for millennia. Are we alone? And if not, where are they? The tantalizing prospect of finding extraterrestrial life, even microscopic, hidden beneath miles of ice, or thriving in exotic liquids, fuels an insatiable curiosity that pushes the boundaries of engineering and scientific inquiry. It's not just about discovering strange new worlds, it's about fundamentally reshaping our understanding of life itself. Are the principles that govern life on Earth universal, or are there countless variations yet to be imagined? The moons we've explored tonight are the very crucibles where these profound questions are being tested. A mainstream historical fact is that the concept of the habitable zone around a star, often called the Goldilocks zone, initially focused almost exclusively on planets. But the discoveries of subsurface oceans on moons have significantly expanded our understanding of where liquid water, and thus life, can exist. Can you grasp the profound shift in perspective that brings? Consider the sheer resilience of life on Earth, even in the most extreme environments. We have microbes thriving in superheated hydrothermal vents at the bottom of the ocean, in acidic hot springs, in Arctic ice, and even deep within solid rock. These extremophiles serve as powerful analogs for what life might be like on moons like Europa or Enceladus. If life can withstand such incredible pressures, temperatures, and chemical imbalances here, who's to say it can't do the same, or even more, in the hidden realms of the outer solar system? It's like discovering that your neighbor's prize-winning pet isn't a fluffy poodle, but a badger that lives happily in a dumpster. It makes you rethink everything. The ongoing scientific debate about the definition of life itself becomes particularly relevant when considering moons like Titan. If life on Earth is defined by its use of liquid water, carbon-based chemistry, and DNA, what about a hypothetical life form that uses liquid methane as a solvent, or silicon instead of carbon as its backbone? This isn't just science fiction, it's a serious area of research within astrobiology. The sheer diversity of chemical reactions possible, coupled with the vastness of the universe, suggests that our current understanding of life might be incredibly narrow. One quirky tidbit: some scientists propose that on worlds like Titan, cryovolcanism might be analogous to Earth's plate tectonics, providing a mechanism for resurfacing and cycling materials that could be essential for any emerging life. Historians still argue whether the search for exotic life on worlds like Titan or the focus on water-based life on icy moons offers the more promising pathway for the initial discovery of extraterrestrial biology. Both approaches highlight the openness of scientific inquiry and the willingness to challenge preconceived notions. It's a testament to the idea that science thrives on asking what if, and then meticulously trying to find the answers. The challenge of detecting life on these moons is, of course, immense. We're not talking about little green men waving hello. We're talking about potentially microscopic organisms, or subtle chemical signatures, or even just the remnants of past life. The instruments on future missions need to be incredibly sensitive and capable of distinguishing between biological and geological processes. This is where the concept of biosignatures comes in: specific molecules, structures, or isotopic ratios that are considered strong indicators of biological activity. For instance, an unexpected abundance of certain gases or complex organic molecules with specific chirality, handedness, could be red flags for life. Can you imagine the precision required for such a task? Imagine a future mission to Europa. It drills through the ice, deploys an autonomous underwater vehicle, and this vehicle, equipped with highly sensitive sensors, cruises through the dark ocean. What would it look for? Perhaps unusual concentrations of methane and oxygen coexisting, which would be thermodynamically unstable without a biological process constantly replenishing them. Or maybe complex, self-replicating molecules that don't appear to have a purely geological origin. It's like finding a perfectly constructed, complex machine in a cave. It strongly suggests an intelligent builder, even if you don't see them. The ethical considerations of discovering alien life are also a significant part of the conversation. If we find life, particularly microscopic life, what are our responsibilities? How do we ensure we don't contaminate these pristine environments with Earth microbes? The concept of planetary protection is paramount, guiding mission design and operation to prevent both forward contamination from Earth to other bodies and backward contamination, bringing alien microbes back to Earth.
It's like ensuring you don't accidentally track mud into a perfectly clean house, especially if that mud could potentially reproduce. These considerations are not trivial. They shape every aspect of mission planning, from the materials used in spacecraft construction to the sterilization procedures before launch. The scientific community is united in its commitment to responsible exploration, prioritizing the preservation of potential alien ecosystems over hasty discovery.
The sheer scale of these endeavors, both in terms of scientific ambition and technological complexity, is truly awe-inspiring. We are, in essence, reaching out across billions of miles of empty space, using robotic surrogates to touch, taste, and even sniff for the faintest whispers of life beyond our home planet. It's a testament to human ingenuity and our innate drive to explore the unknown. A mainstream historical fact here is that the entire field of astrobiology itself, which combines astronomy, biology, and geology, is relatively young, formally emerging in the latter half of the 20th century as scientific capabilities allowed for more serious consideration of life beyond Earth. Doesn't that make you feel part of something truly historic? The data gathered from current and future missions will not only help us search for life, but will also deepen our understanding of planetary formation and evolution across the entire solar system. Every piece of information, every image, every chemical reading adds to our cosmic puzzle. Why are some moons so active while others are dormant? How do tidal forces sculpt entire worlds? What are the limits of internal heating and the persistence of liquid water? These aren't just academic questions. They inform our understanding of how our own planet came to be and how it might evolve in the distant future. It's like finding a new piece for a jigsaw puzzle you've been working on for centuries, and suddenly a whole section of the picture becomes clear. Consider the role of the gas giants themselves in shaping their moon systems. Jupiter and Saturn, with their immense gravitational fields, are not just passive hosts. They are active architects, exerting powerful tidal forces that literally knead their moons, generating the internal heat that can sustain liquid water. It's a dynamic, intricate dance, a cosmic ballet where gravity provides the rhythm and the moons respond with geological fireworks or hidden oceans. This symbiotic relationship is a crucial aspect of understanding the habitability of these moons. Can you visualize that incredible cosmic interplay? The ongoing search for life is also profoundly interdisciplinary. It requires the expertise of planetary scientists, biologists, chemists, engineers, and computer scientists, all working together to unravel the universe's biggest mysteries. It's a collaborative effort on a global scale, transcending national borders and fostering a shared sense of wonder and purpose. Think of it as the ultimate team sport, where everyone is working towards the same incredibly ambitious goal. One quirky tidbit: some researchers are even investigating the potential for life to exist in supercritical fluids, a state of matter where gas and liquid properties blend, which could open up even more exotic possibilities for alien environments. Who knew fluids could be so flexible? Historians still argue whether the collaborative nature of modern space exploration or the increasingly specialized scientific disciplines required for astrobiology poses more significant challenges for future breakthroughs. Both are complex aspects of the scientific landscape. Regardless, the collective pursuit of these answers is a powerful force for progress. Finally, let's consider the broader philosophical implications of this quest. If we do find life beyond Earth, even simple microbes, it would be a profound moment for humanity. It would force us to reconsider our place in the universe, our unique identity, and perhaps even the very definition of consciousness. It would be a humbling yet exhilarating realization that we are part of a larger, more vibrant cosmic tapestry. It's like looking up at the night sky and realizing that every twinkling light isn't just a distant star, but a potential home to countless untold stories. The journey we've taken tonight, though confined to the solar system, mirrors humanity's larger quest for understanding. It's a reminder that even in our own cosmic backyard, there are unfathomable wonders waiting to be discovered, worlds teeming with potential, and questions that continue to beckon us further into the dark. The future of space exploration is not just about robots and rockets. It's about expanding our minds, challenging our assumptions, and ultimately understanding ourselves better by understanding the universe around us. The prospect of discovering life, even in the most unexpected places like these distant moons, is a driving force that will continue to inspire generations of scientists and dreamers. It's the ultimate treasure hunt with the biggest prize imaginable.
So, we've journeyed through the incredible diversity of our solar system's moons, each a unique world with its own secrets, some harboring conditions that just might make you wonder if life is already stirring beneath their surfaces. From the deep, salty oceans of Europa and Enceladus, constantly warmed by the gravitational dance with their gas giant parents, to the bizarre, methane-filled landscapes of Titan, stretching the very definition of what a habitable world could be. We've even touched upon the ancient, battered surfaces of moons like Callisto and Rhea, which, despite their quiet exteriors, might still hold vast hidden reservoirs of liquid water, a testament to the surprising persistence of this vital ingredient in the cold embrace of space. Truly, the universe has a way of surprising us, doesn't it? The ongoing search for extraterrestrial life is perhaps the most profound scientific quest humanity has ever undertaken. It forces us to reconsider our place in the cosmos, to challenge our anthropocentric biases, and to truly open our minds to the countless possibilities that the universe holds. It's no longer a question of if we find life beyond Earth, but when and where. The technological advancements, from sophisticated orbital probes that can peer beneath miles of ice to intrepid landers designed to taste plumes or hop across alien terrains, are bringing us closer than ever to answering this ancient question. Imagine the headlines, the profound shift in human perspective, the moment we truly grasp that we are not alone. It would be a moment that echoes through history, forever changing our understanding of existence. A mainstream historical fact here is that the scientific method itself, with its emphasis on observation, hypothesis, and experimentation, is the very tool that allows us to approach such monumental questions with rigor and confidence, guiding us through the unknown step by careful step. Can you feel that sense of impending discovery? The unique characteristics of each moon, Europa's young, dynamic crust and likely active ocean, Enceladus's constant geysers hinting at hydrothermal vents, Titan's thick, organic atmosphere and methane lakes, Ganymede's intrinsic magnetic field protecting a vast layered ocean, and even the subtle signs of past activity on moons like Dione and Ariel. Each contribute vital pieces to the grand puzzle of habitability. They are not just frozen rocks, they are dynamic systems, miniature worlds with complex geological histories and tantalizing potential. It's like finding a series of nested boxes, each containing a different and equally intriguing surprise. The challenges, of course, are immense. The sheer distances involved mean that every mission takes years, sometimes decades, to plan, launch, and execute. The environments are harsh, with extreme temperatures, crushing radiation, and the vacuum of space testing the limits of our engineering capabilities.
And the detection of life, especially microbial, requires instruments of incredible sensitivity and an even greater understanding of what constitutes a biosignature. It's like trying to find a needle in a cosmic haystack using only the most precise instruments imaginable and still having to figure out what a needle looks like if you've only ever seen thread. One quirky tidbit, the energy required to send a spacecraft to these distant moons is so immense that even a small, relatively light probe needs a launch vehicle the size of a skyscraper to escape Earth's gravity well. Talk about a mighty leap for a little leap. Historians still argue whether the most significant breakthrough in the search for extraterrestrial life will come from direct detection of alien microbes or from the discovery of complex prebiotic chemistry that shows life's building blocks are widespread. Both are thrilling prospects that promise to redefine our understanding of the universe. Regardless of the form it takes, the discovery would mark a new era, an irreversible shift in human consciousness. As you drift off tonight, let your mind wander to these distant, enchanting worlds. Picture the light reflecting off Europa's icy cracks, the delicate plumes erupting from Enceladus, or the orange haze of Titan's atmosphere obscuring its methane seas. Imagine the silent, dark oceans beneath, where unseen forces might be at work, and where life, in some form we barely conceive, might be thriving. These moons are not just objects of scientific study, they are beacons of possibility, reminding us that the universe is far vaster, far more diverse, and potentially far more alive than we can fully comprehend. The cosmos is whispering its secrets, and we are finally learning to listen. The journey continues, even as you rest.